Okay, so our last speaker before the coffee break is Clemens Heuberger from Alpen-Adria University in Klagenfurt, and he will talk about the asymptotics of regular sequences.
Thank you very much, and thanks to the organizers for giving me the opportunity to speak here. So this is joint work with Mario Kurnik, and my apologies to all those who still know everything I said last year at AFA 2024 by heart. So I will speak about regular sequences. I spoke about regular sequences last year, and I still decided to give you an introduction and example for regular sequences for those who did not attend last year's talk, or maybe don't remember perfectly. Okay, so my apologies for that, but then in the second half, there is something which is new. Okay, so I come with two examples. The first example is some divide and conquer algorithm. So I have a list of numbers, say I'd like to find the minimum and maximum by divide and conquer. So one possible algorithm, and the one we are considering here is we partition into two sets of almost equal size. We find minima and maxima in both components, and then compare, and then we are done. And the number of comparisons, when you do that, well, recursively doing that in the larger half, doing that in the smaller half, plus two comparisons for comparing the results. So this is a classical divide and conquer algorithm, and this is one special type of regular sequences, as we will see. Because I rewrite that in even case and odd case. For the even case, these two coincide. In the odd case, they don't. And this is the pattern which will recur, which will come back for regular sequences again and again. So this is example number one. Example number two, which I might have shown at one or the other occasion, is sum of digits, binary sum of digits. So if you have the binary expansion, well, the sum of digits is the sum of digits, and you can write it in a similar way. The sum of digits of n is the sum of digits of n halves, floor of that, plus 1 is n if n is odd. And if you write it again for the even case and for the odd case, you get a similar shape as before. S of 2n is S of n, S of 2n plus 1 is S of n plus 1. So we have this kind of recurrences that I'm going to speak about. And I'll write that in matrix vector form, both of them. So I restart with the same thing I just had. And then I write it as a vector. So my vector v of n shall be S of n 1. And then I can write the recurrence I had up there in matrix vector form. So v of 2n is S of 2n 1. And well, if I want that as a matrix vector multiplication, I write it as a trivial multiplication here. And in the other case, the recurrence has been slightly more complicated. So I have that version of a matrix vector multiplication. So here something interesting happens, here nothing interesting happens. Okay. And this will be crucial for the formulation later on. These matrices which somehow define the sequence apart from the initial values. Okay, so that was sum of digits. And for the other example, it would be somehow some kind of exercise. The vector is now a three-dimensional vector, m of n plus 1. And I can do the same exercise. V of 2n is matrix times v of n. And v of 2n plus 1 is matrix times v of n. So in both instances, I have this same structure. I construct a vector where the sequence I'm interested in is the first component, say. We might have some auxiliary sequences in the other components, so that these matrix vector multiplication thing works out. And this will be the definition of a regular sequence. So if I have a vector valued sequence V, such that, and now instead of 2, I have a base Q, so such that Qn plus R, where R is between 0 and Q, is matrix AR times V of n for all n. So Q is a constant, dimension is a constant, and I have these matrices A0 to AQ minus 1. So the first component of V is called a Q regular sequence, or a sequence is called Q regular if I can find a vector valued sequence such that, and so on and so forth. The definition is quite classic by Alouche and Shellitten, 1992. There are lots of examples, even in their first papers on it. And this is the class of sequences I speak about today, and I'm thinking about a little bit. Okay, and so we are interested in the analysis, in the asymptotic analysis, and this is a result by Dumas 2013 and Daniel Krenn and myself 2020, where we take a Q regular sequence, which is the first component of some V of n, and we have an asymptotic formula for the summatory function. So the sum of xn, n from 0 to n, is some expression I'll speak about, plus O of something. So I have an asymptotic expansion for the regular sequence, for the summatory function with, well, all kind of stuff in here. So we have some finite sums here and here, some functions, and so on and so forth, plus an O term. If phi lambda k are suitable one-periodic functions, here we have n to some exponents, which we don't know yet. Here we have some logarithmic terms, factorials, these periodic fluctuations, and an error term. So the only question here is, well, what do we know about these exponents? What do we know about the periodic fluctuations? What do we know about the O term? And things like that. So, well, let's start with that sum here. C is simply the sum of the matrices which govern the sequence. Sigma of C is the spectrum, the set of eigenvalues. So this here is a sum of eigenvalues, but I'm only considering large eigenvalues. Eigenvalues larger than R. The point is that I have an n to the log q of R here. So smaller eigenvalues would go into the error term, and it wouldn't make sense to list them explicitly up here. Okay, so these are the eigenvalues. What's R? R is the so-called joint spectral radius of these matrices, A0 to AQ minus 1. So what's the joint spectral radius? Take all possible products, normalize by 1 over k. If you have k products, take these norms and take the supreme of all that for k going to infinity. So this gives the size of these A's, or products of these A's. So this here somehow limits what's out of the error term and what's in the error term. So everything which is below the joint spectral radius goes into the error term, everything else is out. Okay, and then we might want to know what is this MC of L. So how many logarithmic factors do we have? Well, the size of the largest Jordan block of C associated with lambda gives the number of logarithmic terms. So as soon as you have the matrices, as soon as you have C, you compute your eigenvalues. Computing the joint spectral radius might be somewhat nasty, but still everything is basically explicit. So the point is, for the summatory function of a regular sequence, we have a result, and it's quite detailed. Okay, a few more comments. These phi lambda k are Hölder continuous. the Fourier series converge, and we can compute the Fourier coefficients numerically using the corresponding Dirichlet series. So we know a lot, I think. And the question now is, I was looking at the summatory function of my sequence. And the question might be, well, perhaps we are not interested in the summatory function, but we might be interested in the original function. That is a quite legitimate question. So let's go back to my two examples I had in the beginning. So one was the min-max, divide and conquer, and the other one was the summatory functions. And okay, so we don't see a lot here. I'm very sorry. This is not good. So we don't see the points because the resolution is not good enough. Hope it will get better in the last one. Let's see. No, we don't see a lot. No. So resolution is not good enough. I might try to destroy everything. So, full screen was the problem. Okay. So, what I want to say, if we look at the sum of digits or at the min-max, well, it's, okay, these are the original functions. We might look at the sum of digits. If you see these dots all here, then you don't want to find an asymptotic for that, because finding an asymptotic for these cloud of dots is meaningless. So for the sum of digits, looking for the asymptotics itself doesn't make sense. And you can easily think about it. The sum of digit of a power of 2, this is simply 1. And the sum of digit of the number immediately preceding is arbitrarily high. So for the sum of digit functions, it doesn't make sense to do the asymptotics of the function itself. We should look at the summatory function. However, for this m of n, this looks quite okay. And the sum of digit function looks, the summatory function looks quite smooth. And then we might want to normalize. So if I take m of n divided by n, then I get for the original function, the normalized version, something which makes sense. This looks like a periodic fluctuation somehow, yeah? So we are here between 5 and 8, so it becomes more and more periodic. If we do it for the sum of digits and the summatory function of the sum of digits and renormalize, it also looks useful. So the point is, sometimes it makes sense to look at the original sequence, and sometimes it makes sense to look at the summatory function. That's the message here. And so, okay, now the message is gone again in full screen. The question is, so that's what I said, sometimes everything makes sense in the original function and sometimes it doesn't. So questions. Does taking the summatory function a finite number of times always lead to smooth asymptotic behavior? So for the sum of digits, I did it once and then it was fine. And the second question is, can we say something about classes where the original sequence is smooth enough? So I'd like to look at the matrices and say, okay, in that case, I can do something. And well, the other case might be more difficult, I don't know. And the spoilers is, well, taking the summatory function a finite number of times, this is almost always good. I spoke about it last year, and it's not relevant to what I'm speaking about today. So this is only a spoiler for last year. And for the second thing is, there's some kind of specific eigenvector structure. And that's the part which I want to speak about today. So for a specific eigenvector structure, I can do it with the original sequence. This is only a one-way statement, so this is by no means necessary, but it is sufficient. So what do I mean with that, with the specific eigenvector structure? Let's go back to the summatory function. So if I have a function, so a vector valued function v of n, and I look at the summatory function sigma of v of n, then there I can compute, I can show that sigma v is regular. I can give the matrices. The matrices have this shape here. So we have a matrix C, which is always the same. And the BR and AR depend on the residue classes. So I have a triangular matrix. The upper left corner is always the same, and the others somehow change. The C is in fact the sum of these ARs. The BRs are some kind of partial sums. So this is probably well known. So to be on the safe side, I say it's a folklore lemma in that area. But if you want to look up a proof, we wrote up a proof in last year's proceedings. I don't know whether this was new or not. It's not difficult. Basically, if we take the summatory function until some point, while we take full runs of the residue classes, and then some additional terms where we always already have this capital N here and only have the last few summons, then we reuse the recurrence, these AR primes. Here we have the C, here we have these partial sums, and we somehow get an expression like that, where this sigma v of Qn plus R is the C times sigma v of n. So this is the main part plus the additional things. So this is an easy proof. Okay. And before coming to my statement, I'd like to have a look at divide and conquer sequences, as was my first example today. So I'm looking at divide and conquer sequences. X of n is alpha times, for some constant alpha, x of n over 2, floor plus beta times x n over 2 ceiling, plus some pole function. And Shenque Wang, Svante Jansen, and Tsai in 2023 proved that as long as the toll function is small enough, then they have a similar, or they have an expression like I had before. So x of n, the original function, is n to some exponent, periodic continuous fluctuation, plus error term. So they can just say something for the original sequence, and I could only say something for the summatory function. So there might be a very simple explanation for that phenomenon. Well, these two are flageolet lecturers, so they can do more than I can. So, okay, this is a very simple explanation. It was somehow still somewhat intriguing that they could do it and I couldn't. And let's make the connection explicit. Yeah. So if I look at that, I can do what I did in the first example. I can do even case, odd case, write it as in the first example. So this is actually a regular sequence, what they are considering. They are considering a special case of a regular sequence with this toll function. So as long as this toll function is well behaved, we can write it as a regular sequence. Okay, so why is that they can do it and I can't? I gave you the first explanation already. I'll try a second explanation. So, okay. Let's have a look at that. So these two this is the recurrence. I don't look at the total function. I look at these 2×2 matrices. And if you look at these 2×2 matrices long enough, we could compute eigenvectors. And so these are the 2×2 matrices. Everything else is not interesting for us. And they have a common eigenvector. 1, 1 is an eigenvector of both matrices. Alpha plus beta, alpha plus beta, fine. Alpha plus beta, alpha plus beta. So 1, 1 is a common eigenvalue to the eigenvector to the dominant eigenvalue alpha plus beta. This is clearly dominant because alpha and beta are assumed to be positive. So this is the dominant eigenvalue, and they have a common eigenvector. Okay, and if I have a common eigenvector for these two matrices, I can do some kind of common diagonalization. Well, not really diagonalization, but let's do a change of basis. And I'll have such a triangular form where the alpha plus beta is up here and everything else gets some tildes and things like that. So now we have some kind of common structure of my summatory functions with this triangular form C and something else, and there, after basis transformation, form of alpha plus beta 0 and some other matrices. And in both cases, we have some kind of growth assumption. I had the growth assumption that the joint spectral radius of these guys is smaller than the relevant eigenvalues of C. And their assumption was that the total function is smaller than, well, alpha plus beta, which is the only relevant eigenvalue of the upper left corner, because there's only that eigenvalue, because, well, it's a scalar. Yeah? So there is this connection. And then I wanted to see, well, what's happening with my proof in their case? So can we use my old proof for this triangular shape? And indeed, we can. And I have 3 minutes for that lengthy proof, okay? We start with these expressions. I only look at the left eigenvector associated with an eigenvalue of lambda of C, because that's the only thing which is interesting. Everything else is linear combination. So I assume that I can somehow bound the products of the lower right thing. This is related to the joint spectral radius. I can iterate the recurrence so that the Vn is a product of matrices times V naught. So I only have to look at products of matrices. N, well, is written as a Curie digit expansion. And I rewrite that N as Q to the L times X for X somewhere between 1 over Q and 1. So this is a simple technical trick, so that I have somehow the order of growth here and then something which will yield the periodic function at the end. So that's the trick here. Okay. And then, well, I start with that product here. I write it in terms of my axis, so the order changes somehow. Then I have a product of these triangular matrices, so I have to compute the product of triangular matrices. The upper left corner is easy, the lower right corner is easy, and the upper right thing, well, I have a few rounds which I stay in the upper left corner, then I decide to go down to the lower right corner, and this gives this expression here, and that's the crucial expression. Okay, and then, well, I said that W is an eigenvector, so I can replace the C to the L by lambda to the L. This will give my growth factors n to the something at the end. Here I have something And if I look at these guys, at these sum things, here I have a finite sum where we have these big xj's. Then mysteriously, I make an additional assumption b naught equals 0. I could do my joint diagonalization at the beginning or triangulation such that this happens. So I can extend that to an infinite sum, which means that this here will be something which is periodic because it's only x1, x2, and so on and so forth, only these guys in here. So I can write that in some kind of periodic version and then do some more tedious work to rewrite everything in the correct form. This is not spectacular at the end, but I get n to the something which is periodic in the logarithm. So I get that. So what I want to say, this joint structure with this dominant eigenvalue on the upper left corner, this is what really drives our old proof. And then came a surprise. The surprise was we always had these periodic fluctuations to be continuous, even Hölder continuous, nice properties. And this broke down. So we couldn't show that. So first I thought, well, it's my student's fault that he can't show it. One has to find somebody whose fault it is. But unfortunately, there is a counterexample. Here we have a counterexample. I have two matrices which are not too difficult. I can give you these guys explicitly. You can easily check. And indeed, this is certainly not a periodic fluctuation because there is no way a periodic function goes from here up here without anything. So this was somehow the unexpected surprise that we could use the old proof in their case for the two flageolet lecturers, but there's a new phenomenon which we hadn't seen in that context before. And that's the end of my talk. Thank you very much.
Thank you. Any questions?
Did your student find the counterexample or did you?
I told him to find it. So I told him, well, write down the conditions you need. Then he wrote down the conditions. I verified the conditions. Then I told him, well, please give me a counterexample. Then he wrote down a counterexample. I verified again. And now I was sitting on the plane hoping that the counterexample really is a counterexample. And I did these computations here on the plane. So perhaps it's worth double checking. But it really seems to be a counterexample. Does this answer your question?
Yes.
Any other questions? Okay, if not, then let's thank the speaker again. And we are going to have a 32.5 minute long coffee break.
I know the I know.
Yeah, he doesn't infuse, but all the toxic infuse keys are really good story. Remember to every time he grabs me and not stop any numbers. What? No, but you know there's information in all. I'm enjoying everything. And then also it's registered trees. Those pick up trees. That's how we sit down. Learn trees. No, No, I could tell that too. But I always felt that way.
He needs to come from really good. No, it's another way. Every time I get ready, pick one thing. Get good at it.
When I moved from Chile to the US, I loved Madison. They had this picture of that leg, which was a back picture. They made the treatment after. Below it says, know something about everything, and everything about something. And I thought it was the best advice.
Yeah. That feels like a model for AMA in some way. Because of how diverse this is. Yeah. I like that sometimes in the day you get to hear a problem, you get to hear they give you the literature.
Have to go straight to the point.
Yeah.
But that's the thing, sometimes you can speak an hour and say,
Yeah. Not get too deep.
and it's really 12 minutes because there are questions.
Yeah, exactly. Yeah. But maybe I don't know. Maybe I have a bad thing to say. I don't really because I find also sort of improve sometimes. If you look away for 1 second, you come back and find change. Yeah, just like that. Yeah. I'm happy that I am.
Yeah,